Hey guys, so let's look at 7.3. We're going to see two new sets of identities. We're going to start with double angle and then we're going to look at half angle identities. I'm going to show you how the problems look when you're using these to solve certain specific valued problems. And I'm going to show you how to use them when you're verifying some identities or simplifying expressions. All right, so I'm going to start by giving you what we call the double angle identities. So you guys notice a double angle would be like to find the sine of 2x. So you take your angle x and you double it. Usually, in this case, you might know the sine of x, but you want to know the sine of 2x. So this is how this identity works. So if you're looking for the sine of 2x, it ends up equaling 2 times the sine of x times the cosine of x. So it looks like if you know the sine and cosine of the original angle x, you can find the sine of double that angle, so the sine of 2x this way. Just beware that sine of 2x is not just finding the sine of x and then multiplying it by 2. That's a different thing. So sine 2x equals 2 sine x cosine x. The cosine of 2x, you guys, is a little different. To find the cosine of 2x, you can do cosine squared x minus sine squared x. And you guys, these formulas actually are derived using the sum and difference identities. And again, not going to explain them in the video. If we were in person, I probably would. But to keep it as succinct as possible, I'm just giving you the formulas. Now, cosine of 2x is cosine squared minus sine squared. Don't get this confused with the Pythagorean identity. Remember, there's a plus there. Cosine squared plus sine squared does equal 1, but you guys, cosine squared minus sine squared is a different value. It's the cosine of 2x. And you guys, using Pythagorean identities to change these expressions, we actually have two more variants of cosine 2x. So you guys, one of them is 2 cosine squared x minus 1. And then another version would be 1 minus 2 sine squared x. And you guys, these are found by taking this one, using the Pythagorean identities to either replace the cosine or the sine with a comparable expression. But you guys, for the cosine of 2x, all of these identities work to find your answer. A lot of times it depends on what you're given. Let's say you're working a problem and you need the cosine of 2x and all you have is the cosine of x. Well, I might use this one because this one doesn't require the use of sine and I may not know sine. Or vice versa with the sine one. Sometimes when we're verifying identities or proving identities, either of these, you might pick the one that most looks like what you're trying to verify or something like that. But you have 3 to pick one. Sine 2x only has the 1. And you guys, we also have a tangent identity. And you guys, we don't use this one that much because if you do know the sine and the cosine, remember it's real easy to find a tangent by just doing sine over cosine. But if you have to use it maybe in simplifying an expression or verifying an identity, it is 2 tangent x over 1 minus tangent squared x. So it's here, you want to write it down just in case you do end up having to use it. Okay, so make sure you have these written down because I am going to erase them so we can work some problems. And then you can reference them while I'm working the problem so you can see where I'm getting my values. Okay, so get them written down. And let's work some examples using these double angle identities. When you're doing your ALEKS homework on double angles, you're not going to be given the value of x, so you're not actually going to know the specific angle. What it's going to give you is more like some of the problems you did in chapter 5. It's going to say, hey, the sine of x is this value. What's the sine of 2x? It's going to be like that. So x, we never really know what the angle is, and that's all right because we're looking for the sine, cosine, or tangent of those angles. So let me get out my first example. So here's what I'm given. I'm given the sine of x is -1 over root 10. And yes, it does give it to me like this in the problem. I know this has a root in the denominator, but this is the way it's given. So here we go. -1 over root 10. You guys, when you're working these problems, you also need to know what quadrant x is in. So no, we don't have to know what the angle is exactly, but we do need to know the quadrant because we're going to have to find other values for this angle. This one's in quadrant 3. So this is the information given. And I need to find sine of 2x, cosine of 2x, and tangent of 2x. So I need to find all three. Now, all I have so far is this sine. Let's remember how to find the sine of 2x. So remember that identity I just gave you. Sine of 2x is 2 times sine x cosine x. So to use this formula, I have to know the sine of x, which I do have here, but I also have to know the cosine. There's no other version of this formula where I can get away with just knowing the sine. So because I have to know the cosine, I need to find some more values. And guys, this is just like what we did in chapter 5. Think about x, y, and r. Think about what I'm given here. So if the sine is 1 over root 10, negative, what values am I given? Sine is y over r, right? So that means I'm given that y must equal 1 and r must equal root 10. Now, my fraction is negative. Do I put it on top with the y or do I put it on bottom with the r? Well, you guys remember, r is always positive. So because of that, the root 10 stays positive. The y must be -1. If you have y and r, can't you solve for x? Yeah, so remember, x squared plus y squared is always equal to r squared. So let's do a little solving here. I'm looking for x. X squared plus -1 squared equals the square root of 10 squared. So x squared plus, remember, -1 squared is positive. So x squared plus 1 equals, you guys, what's the square root of 10 squared? Remember, the squared and the root just cancel each other out and you're just left with 10. So x squared plus 1 equals 10. I'm going to have to move this somewhere else so we can finish solving that. Okay, x squared plus 1 equals 10. I'm moving it up here. I'm going to subtract 1 on both sides. When I subtract 1, I get x squared equals 9. To get x, I square root both sides, and I get plus or minus 3. How do I know if x is plus 3 or minus 3? You guys, that's why we know the quadrant. We're in quadrant 3. X there is negative. So, x is -3. Alright, so y is -1, x is -3, r is root 10. Remember my goal here. I have to write this again because I erased it. Sine 2x. I needed 2 times sine x times cosine x. What I was looking for was cosine x. Do I have enough information to know cosine x now? Absolutely. Cosine is x over r, right? So the cosine of x is going to be -3 over root 10. And I'm just going to leave it like that. We're just going to use it in this formula, so no need to rationalize. This isn't our final answer. Okay, so if I know that that's cosine, let's finish our identity here. Okay, 2 times sine x. What was sine x? Oh yeah, it was given. So 2 times -1 over root 10 times cosine x. We just found cosine x. It's -3 over root 10. So you guys, from here, all you have to do is multiply. These are both fractions, so we can make this one into a fraction also. Straight across the top, straight across the bottom. 2 times -1 times -3, those negatives cancel out, we get +6 on top. On the bottom, 1, √10 times √10, that's the same as √10 squared, right? So it's just going to be 10. So I get the cosine of 2x is 6/10, and I'm going to reduce that to 3/5. Sorry, that was the sine of 2x. I said that wrong. What we just found was the sine of 2x, and it's 3/5. You guys, one thing that might worry you is that x is in quadrant 3, and I just got a sign that was positive. You guys, remember, that's okay because what I solved for wasn't the sine of x, I solved for the sine of 2x. X might be in quadrant 3, but 2x is going to be in a different quadrant, right? So whatever you get here, whether it's positive or negative right here, is your answer. You don't have to think about whether it's plus or minus. Okay, so I just found the sine of 2x equals 3/5. So I'm going to write that up here. It's an answer we found. Now what else did I need? Well, I needed the cosine of 2x. So I'm going to use my double angle identity for cosine. Remember, I have 3 to choose from. Now, I already have both sine x and cosine x. So I had sine to begin with, and then I solved for cosine. So when I'm thinking about what formula to use, since I have both sine and cosine of x already, it really doesn't matter which one I use. I can use the one that has both sine and cosine in it if I want to. And you guys, it's usually the one that comes to my mind first, so that is the one I'm going to use. When you are writing this down, because this is a minus, you have to be careful of your order. Make sure cosine squared does come first, and it's always minus sine squared. But here we are. Now, I already found the values for sine and cosine, right? So I can just plug them in now. Remember that cosine of x, I just solved for that. It was -3/√10. Sine x is given, and it's -1/√10. These are the only 2 things I need to know to finish this out. How do you find cosine squared? Remember, you take the cosine of x, and then you square it. So the cosine of x is -3/√10. I'm going to square that fraction. So this is cosine squared x. It's the cosine of x squared. Minus, well, the sine of x is -1/√10. And I'm going to square that. So here's the cosine squared x minus sine squared x. You guys remember when you're squaring a fraction, you square the top and you square the bottom. So on top, this is -3 squared. Make sure you remember that that negative squares out, and this is +9. The square root of 10 squared, we've seen that a lot today already, so we know that's going to be 10. So 9/10 minus, over here, -1 squared is +1. √10 squared, oh, I'm writing the root again. √10 squared is 10. So you guys, now I need to subtract. I've got 9/10 minus 1/10. You guys, what's nice about this is usually these are going to be common denominators already for you, so you don't have to worry about that. And you can just do the subtraction. So I have 9/10 minus 1/10, and I get 8/10. Reduce that to 4/5. So the cosine of 2x is 4/5. Now remember what I said about tangent. I have a formula for tangent 2x, but if you already know the sine of 2x and the cosine of 2x, it's a lot easier just to use the quotient identity, right? Tangent is always sine over cosine, so that's what I'm going to do. So to find the tangent of 2x, well, that's just the sine of 2x over the cosine of 2x. Now, when you do this, make sure you are using the sine and cosine of 2x, the one you just found, not just of x. Anytime you're using an identity, this can be whatever it is, as long as it's the same everywhere. So the tangent of 2x isn't sine x over cosine x, of course. Everything has the 2x. But I do know the sine of 2x. It's 3/5. The cosine of 2x was 4/5. You guys, what happens when you have the same denominator in a complex fraction? You can cancel them out. And your answer for the tangent of 2x is 3/4. So you guys, we found these just using the sine of x and knowing what quadrant it was in. So you're going to have a lot of problems like this. So things to remember on them. Remember where your x and your y and your r belong in each of these ratios. It's going to give you 2. You solve for 1. If you know all 3, then you can find sine, cosine, tangent, whatever you need. Remember, when you do that, you're solving for sine, cosine, tangent of x. Then put those values you found into your formulas for sine, cosine, tangent of 2x. It gets a little confusing, guys, but you just have to be really careful. Now, I want to look at one more. I'm not going to solve this one out completely because it solves out a lot the same way. It gives you a different set of information, so I want to make sure that you can get what you need out of what it gives you. So you guys, I looked at an example, and it said the tangent of x was -1/3. And sorry, this negative is right in front. It doesn't assign it to top or bottom. It says we're in quadrant 4. So you guys, again, you're going to find sine, cosine, and tangent of 2x, just like we did. But you guys, what does it give you here as far as x, y, and r goes? Tangent is y over x, right? So when you're assigning which one's y and which one's x, and you have y is 1, x is 3, you have to know where to put the negative. But remember, if we have r in the mix, we always say, oh, r is always positive, so it has to be the other one. But you guys, on this example, we don't have r, so I don't know which one is going to be negative. How do I figure that out? You guys, that's where the quadrant comes in. In quadrant 4, which one's negative, y or x? Y is negative in quadrant 4. So you guys, on this one, you have to know where to assign the negative, even though we don't have that nice fallback where we know that r is always positive. When you solve for r, you'll know it's going to be positive because it's always positive. But I wanted to put that out there. Use your quadrant if you're given a tangent to know which one is negative here. And then from here, you solve as we did in the first question. Okay, so you have those where you use double angle identities to find sine, cosine, and tangent of 2x. And then you also are going to use your double angle identities to simplify or to prove identities. So let me show you one of those. So these aren't solving, they're not finding numbered values, right? These are just like you had in the past. This side equals this side, at least that's what they tell you. You just have to prove that it's true. So 1/2. In parentheses, I have cotangent x plus tangent x equals cosecant 2x. Now you might look at this and say, oh, well, I don't have an identity for the cosecant of 2x. Don't even worry about it. This isn't the side that we're going to be working. It'll work itself out at the end. Remember, when you're proving identities, you can only work one side. If I worked both sides of this equation, I would be assuming that it's true. But if my task is to prove it, I can't assume that it's true until I've actually proved it, right? So that's why we only work one side of the equation. Our goal is to make this side look like this side without touching this side. So usually we start with the more complicated side, right? So I'm starting here. You guys, the first thing I'm going to do, because it usually helps, is I'm going to turn these into sine and cosine. So I have 1/2. Cotangent is cosine x over sine x plus tangent, I know that's sine over cosine, and it still equals this because I don't touch this. All right, so I've got these two fractions. What do I want to do when I have two fractions? Well, I want to put them together, right? I can't put them together as is because they don't have common denominators. I can get that, right? So if one side, or this one has sine as a denominator and this one has cosine as a denominator, what is my common denominator? Well, I really want to take a side note on this. When you're finding common denominators and you don't actually have numbers, well, what do? What if I had this, guys? I have 1 over x plus 1 over y, and I wanted to add them together. Well, what would my common denominator be? You guys, it would be, what is that, LCD, least common denominator? It would be xy, right? Because it has to include both of these factors. So this is how sine, cosine, tangent, all of these trig functions work too. If one of mine is sine and the other one is cosine, my common denominator that includes both of those denominators is just going to be sine, cosine. So it's going to be sine x, cosine x in the denominator. All I have to do is find those equivalent fractions. Okay, so if I want this to have a cosine x in the denominator, I would have to multiply the bottom by cosine x, which means I'd have to multiply the top by cosine x, right? So what we get on top is cosine squared. And on the bottom, I have my common denominator, sine x, cosine x. So what happens on this one? Give myself a little more space. Well, I already have the cosine x on bottom, which means I have to add the sine x on the bottom, which means I have to put a sine x on top. So what do I get on top? Well, I get sine squared. On the bottom, I have that common denominator. Here, yes, it says cosine sine, but it's the same as sine cosine. Equals cosecant 2x. Okay, now that you have common denominators, you can add the numerators, right? So what's my next line look like? I've got the 1/2. Putting these two fractions together, I have cosine squared plus sine squared over sine x cosine x. Hopefully you see it starting to form here. Okay, so I am here. I need to do some erasing to get to my next step. And what's my next step going to be, guys? What is cosine squared plus sine squared? That's just 1, right? So let's use that. I'm going to leave my last line. Okay, so this is where we are. Here, oh, I lost some. This is where we are. This is what that equals using the Pythagorean identity. So this is where we are. You guys were very close. Now that this is just a single fraction and it's as simplified as it gets, just multiply by the 1/2. This is two fractions multiplied together, straight across the top, straight across the bottom. So on top, 1 times 1 is 1. On the bottom, 2 times sine x cosine x is just 2 sine x cosine x equals cosecant 2x. You guys, what is 2 sine x cosine x? It's our new identity for sine 2x, right? So 2 times the sine x times cosine x is otherwise known as the sine of 2x. So what I really have is 1 over sine 2x equals cosecant 2x. Is this true? Yeah, notice they both have a 2x here, so the identities hold. The identity in question here reciprocal, right? 1 over sine 2x is the same thing as saying the reciprocal of sine 2x. What's the reciprocal of sine? It's cosecant. So this is true. Take it one step further. Use that reciprocal identity and write cosecant 2x equals cosecant 2x. Make sure on your last line, I know you've probably gotten it figured out, that your last line looks just like the side you were trying to get equal to. Okay, so that's one example of using a double angle identity. This is the double angle identity we used to prove an identity. So yes, we do use identities to prove other identities. Some identities are more useful than others, so the ones that I teach you are ones that have a lot of use. They have a lot of application. The one we just proved, that 1/2 times whatever it was equals cosecant 2x, it's an identity because it's true for all the functions involved, right? But there's a million identities out there. You could make them up on your own if you wanted to. The ones we're proving are the more obscure ones, like, yeah, that's true, but what I'm really looking for here is for you to use the ones that are common to prove ones like that, that just don't really have any real application. They're just somebody sits around making up identities. We have to prove them using the known identities. Okay. So I do want to prove one more identity for you before we move on to the half angles, because this one was a little more complicated, so I want to do it with you. All right, so on this one I have sine 2x, so there's a double angle right there, over 1 plus cosine 2x equals tangent x. So I have to prove this is true. I'm obviously going to work this side and leave tangent the same. So you guys, this one's very clear that we need double angle identities, and that's exactly where I would start. Sine 2x, how can I write that differently? I can write it as 2 sine x cosine x. So you guys, in the last identity, I had this and I went back to sine 2x. This time I'm starting with this and I'm going the other direction. 1 plus, now, cosine 2x. Remember, I have 3 choices on how I want to write the cosine of 2x. I could use cosine squared minus sine squared, or I could use 2 cosine squared minus 1, or I could use 1 minus 2 sine squared. So you guys, honestly, you can use any of them because they're all equal to the same thing. But if you choose wisely, you can do this in the least amount of steps. So when I'm choosing this, I think about what I have over here. I have a tangent. What is tangent? It's sine over cosine, right? So on top, I have a sine here, and I do have a cosine. I can't really do anything about that, but for tangent, it's just a cosine on the bottom, right? So why don't I use the one that just has cosine? I think it'll get me there to the end faster than if I used one of the other two. So I'm going to use the 2 cosine squared x minus 1 version of cosine 2x. If you don't pick the right version, it's okay. It'll, like I said, it'll just take you more steps to get there. This will get us there quickest. All right, so what do I have here? I have a 1 and then I have a minus 1. So you guys, those are going to cancel out, and I'm looking at 2 sine x cosine x over just 2 cosine squared x. Okay, so let's cancel stuff. These 2's, top and bottom, cancel them out. I can cancel out 1 cosine, right? This has a cosine, this has cosine squared. So when I take a cosine out of it, it'll just take the squared off. So what is left? Well, there's no 2's. There's a sine x on top and a cosine x on the bottom. It sure looks to me like sine x over cosine x equals tangent x. Obviously it does. So my last line, I call it tangent x. And there we go. So that one was actually really short. Why is it complicated? Well, it's because if you choose a different version of this, it'll take you a lot longer. So, like I said, you'll still get to the answer. I want you to get in the habit of picking wisely on those cosine 2x identities. Okay, so let's talk half angle identities. You don't have to prove any identities using these half angle formulas, which is good because they're kind of weird. They're a little more complicated. Definitely not my favorite set of identities. But you do have to answer or solve some problems using the half angle. So I'm going to start by giving you the half angle identities. So I've got, half angle. So double angle was 2x, right? So how could I write half angle? I'm going to write it as x over 2. So the sine of x over 2 equals, and right off the bat you can see why these aren't my favorite, equals plus or minus the square root of a fraction, guys. So plus or minus the square root of 1 minus cosine x over 2. So gross, right? Let's look at cosine. Cosine is actually very similar to sine. The cosine of x over 2 is plus or minus the square root of 1 plus cosine x over 2. And you guys, usually it's not the case that tangent is the nicest identity to deal with in a group of identities, but in this case it is. And it comes from, yes, putting sine over cosine, but what you end up getting out here is actually not so bad. And it has two versions. So I could say that it's sine x over 1 plus cosine x. See, that's not bad at all. Or it could also be written as 1 minus cosine x over sine x. So again, if you're interested in the derivation of these identities, we can talk about it office hours. You can Google it if you want to. What I found in my experience is that you just want to know them so you can use them. So that's what I've given you here. Okay, so yes, write them down, put them in your toolbox. Let's use them to solve some problems. So you guys, these problems, so remember when I just did it, you guys, when we did the double angle, we didn't know the value of the angle. We knew like the sine of x, and we found the sine of 2x. We never really knew what x was. These are worded a little bit differently. We actually do know the value of the angle we're looking for. So it's more like the problems we did when we did the sum and difference identities. We're looking for an exact value, sine, cosine, or tangent of an exact angle. So let me get my, let me find my example. All right, so first example. I want to find the tangent of pi over 12. So at first glance, it looks like one of those problems, maybe I just look at the unit circle. And so I go to my unit circle and I realize that pi over 12 is not on it. Of course not. So I'm thinking half angle identities. Where does pi over 12 fit in with a half angle identity? Well, do look at your unit circle. So what you're going to do is you're going to take this angle and think this is half of an angle that I actually know. This is half of what? Well, if you can't see it right off, multiply it by 2, guys. See what it's half of. If pi over 12 is just half of the angle that I do have on my unit circle, why don't I just multiply it by 2? Well, that's 2 pi over 12, but more importantly, that's pi over 6. So, no, I'm not looking for the tangent of pi over 6. I'm looking for the tangent of pi over 12. But because this is half of this, I can use my half angle identity to find it. So I'm looking for a tangent. I'm going to use my half angle identity for tangent. Doesn't matter which version you use, it really doesn't. Both of them end up being about the same difficulty. So I'm looking for a tangent of pi over 6 over 2. You guys, tangent x over 2, right? Where x is pi over 6. What is the tangent of a half angle? Well, I'm going to use the one with sine on top. Remember, it's sine x over 1 plus cosine x. So in my case, because x is pi over 6, I'm looking at sine pi over 6 over 1 plus the cosine of pi over 6. Doesn't look too bad. I do know those angles because they're on my unit circle. Okay, so what is the sine of pi over 6? Well, it's 1/2. 1 plus, what's the cosine of pi over 6? Well, that's root 3 over 2. So I'm here. So easy values to find. I got to work with this, guys. I've got a root and a fraction in the denominator. I got a fraction in the numerator. You guys, please be careful here. You see a 2 in the denominator here and a 2 in the denominator here. You can't cancel those out like we have been doing because of this. You guys, so keep this in mind. This 1 plus makes that whole cool, oh, cancel out the denominators because they're the same thing. That prohibits that. What I can do though is fix the fractions. So you guys, I've got fractions in both top and bottom. So my first goal is to make those not fractions. Could I multiply both the top and bottom by 2 and get rid of those fractions? Absolutely. So I'm going to take this over here. So you guys, on top I have 1/2, multiply it by 2, now I just have a 1 on top. So that's nice. You guys, when you multiply the bottom by 2, you do have to make sure you multiply both terms by 2. So instead of 1, this will be 2 plus. Instead of root 3 over 2, you're multiplying it by 2, so that cancels out, and you have 2 plus root 3. Okay, so this looks all right, but we need to rationalize the denominator. So remember, we had some problems when we were doing sum and difference that Alex didn't mind that we had a denominator with a root in it. Alex minds on this one. No rhyme or reason, guys. So I am going to show you how to rationalize this denominator. If it was just this, what would I do? I'd just multiply top and bottom by root 3, right? We're good at that, but it's not just that. It's a whole 2 terms here added together. So if you do have this situation where you have a whole number plus a root or a whole number minus a root, and you need to get the root out of the bottom, it takes a little bit more to rationalize it than usual. We actually multiply the top and bottom by the conjugate of this term. What does conjugate mean? You guys, if I have a plus b, the conjugate of that equals a minus b. These 2 terms stay the same. All you do is change the sign in the middle. So, for example, if I have 2 plus root 3, but I need the conjugate, it's going to be 2 minus root 3. Make sure you don't change the sign of this number or this number. All you do is change the operation in the middle. These stay exactly as is. So, top and bottom by the conjugate of this term, 2 plus root 3, I'm going to multiply the top and bottom by 2 minus root 3. So we could have done this on the sum and difference ones, but again, Alex didn't require it. It let you keep a root in the bottom on that one. But here we are, we have to do it now. So top and bottom by 2 minus root 3. Let's see what that ends up being. Well, 1 times anything is that thing, right? So on top, we just have 2 minus root 3. Now, how do I deal with this? Well, I've got two binomials. So binomial, it has two terms in it, right? Multiplied together. How do I multiply things like that? Well, I use FOIL, right? So we haven't had to FOIL in a while, but here we are FOILing. So remember, FOIL is just a fancy way of saying everything over here multiplied by everything over here. So we use the letters F for first. So the two first terms, 2 times 2 is 4. O for outer, the two outside terms, multiplying together, 2 times negative root 3. Well, that's just going to be negative 2 root 3. Remember, you can't actually multiply those together, you just put them next to each other. I, so FOI, I for inner terms, these two. Positive 2 times positive root 3, we get a plus 2 root 3. And then the two last terms, root 3 times negative root 3. So it's going to be negative, but root 3 times root 3 is just 3. So you guys, the reason why we multiply by the conjugate is because when you FOIL, this term here, this root, cancels out. So any term that still has a root in it cancels out. That's what the conjugate does when you multiply it with FOILing. Okay, so I had minus 2 root 3 plus 2 root 3. So the root 3's are gone. What is left? Well, on top I've got 2 minus root 3. On the bottom I have 4 minus 3. So I just have 1. And my answer is just here, 2 minus root 3. So you guys, the half angle formula in itself wasn't that bad. It was the writing the answer, right? So it takes some practice. Just remember, anytime you need to rationalize two terms like this on the bottom, multiply top and bottom by the conjugate and FOIL carefully. All right, we're going to do one more. This one's going to be a sine or a cosine. I can't remember which that I wrote down. It's a cosine, guys. This one's in degrees. It really doesn't matter if you're in radians or degrees on these. Your answers are just numbers, right? But it's going to give it to you both ways. Luckily, we have that unit circle that has both degrees and radians on it, so we know what angles we're looking for. I want to find the cosine of 157.5. So just like with the last one, you want to look at this angle and think about what it's half of. You guys, so I looked at pi over 12, and I was like, oh, that's half of pi over 6. What is 157.5 half of is what I need to figure out. Well, how do I do it? Multiply it by 2. What do we get, guys? 315. So 157.5 could be written as 315 over 2. X over 2, guys, cosine of x over 2, where x is 315. So that's what we're looking at here. We're going to be on our unit circle looking at 315. I need to go to my list of identities and find the cosine of x over 2. So the half angle identity for cosine. So the cosine of 315 over 2 equals, so it's a plus or minus, it's a square root. It's 1 minus cosine of x, remember x is 315, over 2. And then I start putting in values. So, plus or minus, big square root. What's the cosine of 315? So it's in the fourth quadrant where cosine is positive. Be careful, this minus is a minus no matter what happens here, right? So 1 minus positive root 2 over 2, that's the cosine there, over 2. So this is all, let me clarify, this is all under a square root. So what in the world do I have here, right? A fraction with a fraction in it, with a root in it, under a big root. Awesome, right? Okay, so let's figure it out. How do I want to write my answer? So the first thing I want to do, just like the last one I did on the tangent, I've got a fraction within a fraction here. I can't just use my ideas for complex fractions because of this 1 minus attached to it, right? So why don't I multiply top and bottom by 2 again, like I did with that tangent problem, to get rid of this fraction. So I haven't done anything with this square root. All I've done is multiply top and bottom by 2. Remember, you have to multiply this by 2 also. So I have 2 minus root 2. That's what's left there. And on the bottom, multiply that by 2 and I get 4. So let me bring it over here. Okay, so I'm at plus or minus square root of 2 minus root 2 over 4. So what I'm actually, I don't even need that on this line because I have it down here. So you guys, do I have a root in the denominator here? No. I have one in the numerator, but remember, that's fine. So you guys, this is actually a totally fine version of my answer. All I need to do is possibly take this root if I can. So this is what it's going to look like. Remember, when you have a fraction, whether it's a power or a root, you do it to the top and you do it to the bottom. So while I can't really take the root of 2 minus root 2 and get an exact number, I can take the square root of 4, right? So my answer ends up being plus or minus. I leave the square root on top because I can't actually take the square root of that. But I am going to take the square root of the bottom. Notice it's not in the root anymore. The root's only on top. And I have a 2 on the bottom. Now, yes, I have a root within a root. That's just the way it's going to be, guys. To keep this one exact, that's as good as it gets. Now, problem, plus or minus. How do I figure that out? It didn't tell me what quadrant I was in before, but I think it did something better. I actually know the angle value, right? Remember what you were looking for was the cosine of 157.5. And it is this plus or minus root 2 minus root 2 over 2. That's what you found. Is it plus or minus? Well, where is 157.5? That's in the second quadrant, right? What is cosine in the second quadrant? It's negative. So there we go. All right, so there's our answer, guys. That wraps up 7.3 for you. As always, you got questions, I've got answers. Hit me up in the Zoom office hours, or we can always schedule our own Zoom meeting if you email me, and we can go over stuff.